Hello dear students, welcome to the class. So we are discussing the chapter semiconductors, where in the previous class we have discussed about the forward biasing. With the help of the two substrates P and N type, by marking, otherwise the drawing the depletion region, I have explained you what exactly is going to happen in the forward biasing, and hence it is going to support the conduction. Forward biasing of the diode, basically conduction of the current. Okay. Now we'll be studying the reverse bias. Now we study reverse bias. We'll be studying the reverse bias of junction diode. What we are studying, basically we are studying the normal diode, junction diode, which appears like this. That means it's a symbol inside this. Symbol is like this. Okay. So we are studying the junction diode, which is just a normal, otherwise the simplest form of a diode that is formed with joining the P and N, otherwise a single silicon, otherwise germanium bar, otherwise substrate, is doped with trivalent impurity one side and pentavalent impurity other side, resulting into one P region and one N region. The contact, otherwise the separation of the P and N, the region is called as what? The junction. Okay. Under unbiased condition, that means when the diode is not biased, when the diode is not applied with any external energy, the diode inside it is going to form a depletion region, otherwise a depletion layer, which is basically the deposition of the immobile ions, negative ions at the P side, positive ion at the N side. Okay, the P side negative ions are called as what? Acceptor. The positive towards the N type, the immobile ions are called as what? Donor ion. Okay. Yeah. So basically, these are deposited near the junction. Near the junction, that layer of the deposition of the immobile ions is called as what? The depletion region. Here, and that depletion region is going to play a very important role in the forward bias as well as in the reverse bias condition. Overall, the operation of the diode. In the forward bias, we have seen that depletion region keeps on reducing or shrinking. Hence, at some point that is beyond the okay, that depletion region with respect to its width and its height, it is going to give a barrier potential. Clear? With respect to its height. Okay, and the height we have considered like this, right? So suppose this is the depletion region. Height is considered to be like this. That means we can say it as a diagonal. Okay. So in that case, the width is also important. As the width increases, also the height is going to increase. And this height is nothing but the barrier potential. The height itself is what? Barrier potential B. Here. So all this we have studied, and now these concepts we will be studying for the reverse bias condition. What happens to this height? What happens to the width? What happens to the overall depletion region under the reverse bias condition? Right. So the same depletion region will be considering now with the application of what? Opposite polarity of the batteries. Like we have connected the positive terminal of the battery to the P region, negative to the N region for our forward bias. Exactly the opposite will be connecting for the reverse pass connection. That means the P type will be connected with the negative battery, negative of the battery terminals, and the N type will be connected with the positive of the battery terminals. So for that, I am first of all drawing the figure with the depletion region, and at the depletion region the position of the immobile ions, and also the P type and N type showing the majority and minority charge carriers. Okay. Here the position of the immobile ions. Immobile ions, donor, that means positive ions, P N type, acceptor, that means negative ion at the P type side. Along the hole, along the hole, along the hole, along the hole, right? One hole for each acceptor ion and thermally ejected few electrons. Those are termed as the minority charge carriers for this P type. So this is the depletion region, this much depletion region which is already existing. It is not yet in the under effect of any forward or reverse. Okay. Now we are applying the reverse pass. Negative terminal of the battery is connected to the P type. This is P type, right? And this is the N type. And positive of the battery terminal is connected to the Now what happens? Again, I am just recalling P type, majority charge carriers and minority charge carriers, holes and electrons. The N type, exactly the opposite. Majority and minority. Electrons and holes. Here. So now the majority charge carriers here are what? The holes, and holes are positive, electrons are negative charges. Here. So battery is having what? Negative charge. Negative charge is going to attract the positive charges. So all the holes will be attracted by the negative terminal of the battery. Likewise, all the electrons are attracted towards the positive terminal of the battery. Here, as in the case of our pairs, they were repelled. Now they will be attracted because exactly opposite connection is made now. In previous example, positive terminal was connected to the P type, negative terminal was connected to the N type. Hence, all the positive charge in the battery repelled the positive charges inside the P type. That is, it repelled all the holes. Okay. Whereas the negative terminal repelled all the electrons. As a result, the width of the depletion region reduced. Here what is happening, all the holes are attracted. Holes are attracted and electrons are attracted by positive. Holes are attracted by the result of the battery. As a result, what happens? These holes move this side. All these holes are moved. Okay. All these holes are moved. Here. Right. So now these immobile ions are also the part of this depletion region. Okay. And they have now become the part of the depletion region. Now this side the depletion region has become wider. Now the width has increased. Here. Similarly, all these electrons are moved towards the positive terminal. Now the width has become this much. So totally, what is happening in the reverse bias condition is that the depletion layer width is increasing. The width of the depletion layer has increased here, and why it has increased? Because holes are attracted towards the negative terminal, electrons are attracted towards the positive terminal. The holes have left their acceptor ion here and donor ion here, and they have moved towards the battery, and those now has become immobile ions. These ions, after losing its hole and after losing its electron, it has become an immobile ion and it is contributing towards the depletion region. Now the depletion region has become wider. The width has increased. Clear? Right. Now what happens? Because the width has increased. What it is called? It is called as diode. The width has increased means here we can also see the barrier potential was marked like this, isn't it? The barrier potential was marked like this. That is from negative towards the positive. Yeah. And under the forward bias condition, the forward bias was opposing the barrier potential. Okay. In forward bias, applied voltage V was opposing VB being forward bias. But in reverse, what happens? It is VB V and with VB. Okay. Otherwise it is in the same direction. It is in same direction. As VB. It is in the same direction. Okay. So hence it is not going to oppose it. This V is not going to oppose this VB. So what it is going to happen basically is the VB is going to increase. Why VB is increased? We can also relate it by the width of the depletion region. See, this height has increased now. Height of the depletion region has increased because the width has increased. So the height is nothing but what? We have studied barrier potential VB. Height itself is what the barrier potential VB. As the width has increased, the depletion region has widened. Okay, so the height has increased, hence the VB has increased. VB has increased means no conduction, no free electrons cross the junction, and no holes cross the junction. Okay. In the forward bias condition, what was happening? The wall, the barrier, the depletion region reduced, and beyond the value VB, it was completely ineffective. It was not having any effect over the electrons or holes. So the electrons or holes were freely moving and conducting. Hence the current was flowing through the diode. But in this reverse bias condition, what is happening here is the depletion region has further increased. The depletion region has become wider compared to the normal unbiased condition, it has become wider. In the previous case, it was become uh, it was shrinked. Okay, it was become narrow. So because of that, what happened? The free electrons were, otherwise the holes were able to cross the junction and result into conduction. But now in this case, what is happening? The depletion region has become further wide. BD has increased because the height has increased. Normal, very simple that width is increasing means the wall has become more stronger. Right. The wall which was restricting the holes or electrons to cross the junction has become much stronger. So definitely it is not going to allow any electrons or holes to cross the junction and result into conduction. So the barrier has become stronger, the VB has increased, and it is not going to allow any electrons or holes to cross, and hence no conduction under reverse bias condition. Right. Hence there will be no conduction in the reverse bias condition. So I'm just going to write the explanation now. So what happens in the reverse bias condition? How the reverse bias is formed first. P type is connected to the negative terminal of the battery, whereas N type is connected to the positive terminal of the battery. That is the first condition, otherwise what is called as reverse bias. The meaning of reverse bias. Okay? Reverse bias is formed or established by connecting connecting the negative terminal of the battery to P type and positive terminal of the battery to N type of the. So how does reverse bias is formed? Reverse bias is formed by connecting the negative terminal of the battery to P type and positive terminal of the battery to N type of the diode. Yeah. So now the diode is under reverse bias condition. Okay. So normally if a diode with its symbol is to be connected, right? So it will be connected like this. Positive to cathode, negative to anode. Okay, with the symbol. This is with the formation of the distribution. So this is how the reverse bias is formed. Now what is happening after the reverse bias is formed? Okay. So negative terminal is connected to the P type, positive terminal is connected to the N type. The holes in the P type are attracted towards negative terminal of battery. Okay. Likewise, electrons in n type are attracted towards positive terminal of battery. Positive terminal of battery. Right? Yeah. So due to this, what happens now? Due to this action, due to this, more accept ions are deposited at depletion region near depletion region at P type. Okay. Acceptor ions at P type and donor ions, more donor ions, more donor ions are deposited near depletion region at N. Here. So what is happening? First of all, what is reverse bias is? Reverse bias means when the negative terminal is connected to P type and positive terminal is connected here. That means higher potential is connected to N type, lower potential is connected to P type. The holes in the P type are attracted towards the negative terminal of the battery, and electrons in the N type are attracted towards the positive terminal of the battery. Due to this, more acceptor ions here, more acceptor ions are deposited near the distribution at P type. More donor ions are deposited near the depletion region at N type. Right? So what is happening due to this action? As a result, the depletion region width increase. So what it is basically doing is, it is width of the depletion region. Here, width of the depletion region is increased. One more important point, the applied voltage and barrier voltage VT are in similar direction. Otherwise, the applied voltage is in favor of VP. Does not oppose, that means. Does not oppose. Yeah. It is not going to oppose the, what we can say, the barrier potential. Otherwise the VP. So the VP is increased. The depletion region do not allow electrons or holes to cross the junction, hence no current flows. No current flows. Hence there will be no flow of current in the reverse bias condition. So these are all the important points in the reverse bias condition. Holes are attracted by the negative terminal, electrons are attracted by the positive terminal. As a result, the width increases. Due to this, what happens? All the acceptor ions are deposited here, donor ions are deposited here, more ions are deposited. As a result, as more ions are deposited, what is happening? The width, basically the width is increasing. As the width is increasing, definitely the VB increases, the direct potential, otherwise the barrier, the depletion region has become much stronger. As a result, it will not allow any electrons or holes to cross the junction. So, as the electrons and holes do not cross the junction, there will be no conduction of current. There will be no flow of that means hence no current flows. Okay. Here, this is the operation, the entire working of the reverse bias. Okay. This question can be asked for 5 marks. Otherwise, minimum for 3 marks to explain the operation of reverse bias condition in the junction diagram. Now, reverse saturation current. Reverse saturation current. So definitely applicable to the reverse bias itself. That's why I have not erased this. Right? For this explanation, there is no need for this figure, even though I am taking it to explain the reverse saturation. This is very important, the reverse saturation current. Okay. So what happens in this reverse saturation current is holes and you are in the electrons. Your electrons and you are in the holes. That means minority charge carriers. While talking about the majority and minority charge carriers, I have told you that minority charge carriers are very important to understand few concepts, right? So here, what are the minority charge carriers? Electrons. And here, holes, isn't it? So, what happens even though all the holes are attracted towards the negative terminal, but this electron, which is negative, will be repelled by the negative terminal. Likewise, the holes here and there, these are thermally ejected electrons and holes. The minority charge carriers are basically thermally ejected ones, right? So what happens? This battery is acting as a reverse bias to the majority charge carriers, but at the same time it is acting as a forward bias to the minority charge carriers, isn't it? To the majority charge carriers, so the same battery is acting as a reverse bias, whereas it will be acting as a forward bias to the minority charge carriers. Here. So, as it is acting as a forward bias to the minority charge carriers, very few electrons and very few holes move, otherwise conduct, resulting into a very small amount of current in the form of microamperes. This current is known as what? The reverse saturation. So what is this reverse saturation current? The reverse saturation current is a very small current under reverse bias condition due to minority charge carriers. Here. So what is this reverse saturation current? It is the very small amount of current resulting due to minority charge carriers under reverse bias condition. Right? So, I'm writing about the reverse saturation current. Under reverse bias condition, under reverse bias condition, the reverse bias sorry, the reverse bias acts as forward bias to the minority charge. In the reverse bias condition, the reverse bias acts as forward bias to the minority charge, and as a result, what happens? As a result, a very small amount of current flows called reverse saturation. Called as what? Reverse saturation current. Called as the reverse saturation current. Under reverse bias condition, the reverse bias acts as forward bias to the minority charge carriers, isn't it? As a result, a very small amount of current flows called reverse saturation current. So how you will define reverse saturation current? Reverse saturation current is defined as a very small current in terms of microampere. A very small current flowing under reverse bias condition. Flowing under reverse bias due to minority charge factors. Due to what? Minority charge factors. Okay. So reverse saturation current. Now this reverse saturation current is in order of 1 microampere for silicon and 10 microampere for germanium. Right? The minority charge carriers are thermally generated charges. Thermally generated charges. Okay. Hence, they are very sensitive to temperature. And they are very sensitive to temperature, and as temperature increase, reverse saturation current increases. Increases. Reverse saturation the minority charge carriers are thermally generated charges. Okay, hence they are very sensitive to temperature. As temperature increases, reverse saturation current increases. Yeah. So this is about the reverse saturation current. It will be asked in its definition, what is reverse saturation current? So reverse saturation current is a very small amount of current flowing under reverse bias condition due to minority charge carriers. 3 points you need to remember about the reverse saturation current. Very small current under reverse bias, right? And due to minority charge carriers. These 3 important things you need to always remember about the reverse saturation. So this is about the reverse saturation current. Now we'll next reverse breakdown. What is reverse breakdown? And reverse breakdown voltage. Right? So now, what is the reverse breakdown? Reverse breakdown. Again, the term reverse, so it is also applicable to the reverse bias. So it is for reverse bias only. Depletion region widens has become wide. Hence, no current flows. Hence, no current flows. And we are talking about reverse bias. Okay. For reverse bias, depletion region has become wide, hence no current flows. But very small current flows due to minority charge carriers. Due to minority charge carriers. Reverse saturation current, that is called as reverse saturation current, and this reverse saturation current is sensitive to temperature. Okay. So obviously know for the reverse bias condition what all happens in the reverse bias condition, depletion region has become wide, hence no current flows, but very small current flows due to the minority charge carriers, so the saturation current is sensitive to temperature. As temperature increase, the reverse saturation current is written as I naught. Okay, I forgot to say that there. So we will represent it by I naught. Reverse saturation current I naught. Okay. So as temperature increases, I naught increase, and as I naught increase, temperature increases. So due to this cyclic process, okay, due to this cyclic process, what happens is sudden current starts flowing Abruptly. Abruptly. Otherwise, abruptly current starts flowing. A large current starts flowing. Abrupt means which cannot be controlled. A large current starts flowing. Abruptly, a large current starts flowing. Okay, and this is due to the increase in the temperature and hence increase in the reverse saturation current and again increase in the temperature and again increase in the reverse saturation current. So it is basically depending on the temperature and it is happening due to the temperature itself. A large current flows, starts flowing. Okay, here at the voltage, otherwise the voltage at which the voltage at which a sudden large current starts flowing is called reverse breakdown voltage. Otherwise, simply breakdown voltage. Is called what? Reverse breakdown voltage. Termed as reverse breakdown voltage. EBR. Okay. Reverse breakdown voltage. The voltage at which suddenly current starts flowing is called as reverse breakdown voltage. And this happens due to sudden current flows due to break. Sudden current flows due to breakover of the junction. Okay. That means what? All the bonds inside are broken. The covalent bonds are broken. The crystalline structure, inside the crystalline structure, the entire orientation, otherwise the covalent bonds are completely damaged, and hence the diode is damaged. But once the reverse bias is removed, they can be reconstructed. Sometimes if very large current flows and it has completely damaged the diode, it cannot be reformed or reconstructed. So, this is about the reverse saturation current and the reverse breakdown. What happens due to the reverse saturation current? If temperature increases, due to temperature increase, reverse saturation current increases. And due to this cumulative process, otherwise the cyclic process, what happens? Suddenly a large current starts flowing, and this happens at the breakover of the junction. Now the junction has become has broken out. Okay, a breakover of the junction has happened. Okay, what is the meaning is basically inside all the bonds are broken, and the effect of the depletion region is no more existing. But at that point, very large current suddenly starts flowing, right? And the voltage at which this happens is called as what? Breakdown, reverse breakdown voltage. VBR, reverse breakdown voltage. right? So this reverse saturation current or the reverse breakdown. So in the reverse breakdown, what happens? Basically, the covalent bonds are broken inside the crystalline structure. It is basically damaged. The covalent bonds are damaged. Okay, and they can, once the reverse bias is removed, it can be reconstructed. Sometimes it will be completely damaging the diode also. Here, so we have studied what all in today's class. We have studied the reverse biasing. In the reverse biasing itself, we have also covered the two concepts, that is about the reverse saturation current and the reverse breakdown. Breakdown of the junction happens. Okay, the junction formation of the covalent bonds has damaged the crystalline structure. Inside the crystalline structure, it has completely been damaged. Right? So that is going to happen here. Clear? So, in the reverse bias, what is reverse bias? Basically, what we have studied in today's class is basically the reverse bias is whenever the lower potential is connected to P type, that is negative terminal is connected, higher potential is connected to N type, that is positive terminal is connected to N type, it forms a reverse bias. Okay. Under reverse bias, what happens? All the holes are attracted towards the negative terminal, all the electrons are attracted towards the positive terminal. As a result, what happens? The holes will leave their immobile, their acceptor ion, and electrons will leave the donor ion. As a result, the acceptor and donor ion are deposited at the junction, near the junction, at the N-type donor ions, at the P-type acceptor. So more ions, immobile ions are deposited at the depletion region. As a result, the width of the depletion region increases. Here, as the width of the depletion region has increased, definitely what happens? The height is going to increase. The height is increasing means BB is going to increase. The BB, the barrier potential, has become more stronger. Okay, the external voltage, otherwise the applied voltage, must reduce the effect of the BB. But in case of the reverse bias, it has enhanced it. Otherwise, it has increased the effect of the barrier potential. As a result, the barrier potential has become stronger, the barrier has become stronger, the depletion region has become stronger. So it is going to not allow any type of electrons or holes to cross the junction. Now, no electrons and holes will be crossing the junction. Clear? Electrons or holes are not going to cross the junction because the depletion region, the wall that was restricting the electrons or holes to cross the junction, has become stronger. Right? As a result, what happens? There will be no flow of electrons and holes, hence no current flows under reverse bias condition. Right? So under reverse bias condition, there will be no flow of current. Clear? So this was about reverse bias condition, and moving to the reverse saturation current. The same reverse bias acting to the majority charge carriers acts as a forward bias to the minority charge carriers. Right? As a result, what happens? A few electrons and holes can move within the junction, and they will form a very minute, otherwise very small amount of current called as the reverse saturation. Here, and this reverse saturation current, as the minority charge carriers are thermally ejected electrons and holes, they are resulting due to the effect of heat. They are very sensitive to temperature. Right? So this, as a result, what happens? This reverse saturation current is sensitive to temperature. They are very sensitive to temperature. So as the temperature increases, their value is going to definitely increase. Here, the same concept is applicable to the reverse breakover, otherwise the reverse breakdown. What we say here. So in the reverse breakdown, what happens? As it is sensitive to temperature, increase in the temperature, increase in the minority charge carriers. More minority charge carriers, more increase the temperature. This cyclic process is going to result into what? More reverse current, reverse saturation current. At a point, what happens? Abruptly, a very large current starts flowing, and that happens when the junction breaks down. And the voltage at which this occurs, that means the breakdown of the junction occurs, is called as what? The breakover voltage. Right? It is called the breakover voltage, PBR, which is again sensitive to what? Temperature. So in the breakover of the junction, what is basically happening is the inside the crystalline structure, the bonds, the covalent bonds have damaged. Okay, the entire orientation has damaged. It has disturbed. But just by removing the reverse voltage, we can reconstruct. So this is all about the reverse bias. In the reverse bias, we have studied the reverse bias condition, how exactly inside the depletion region what all happens and how it is going to limit the, otherwise how it is going to restrict the flow of electrons or holes under reverse bias condition. We have studied the reverse saturation current, sensitive to temperature, all that we have studied in the reverse saturation current, and also we have studied the breakover, that is a breakdown that happens in the reverse bias condition. Reverse bias condition and the voltage at which that breakdown happens is called as the VBR, breakdown voltage, reverse breakdown voltage, which is very important. If this a defined reverse breakdown voltage can be a question in your exams. Okay, so in that case, what you are going to write, under reverse bias condition, the voltage at which the junction gets damaged, otherwise the voltage at which a very high current starts flowing is called as the reverse breakdown voltage. Yeah, right. So completely about the reverse bias we have studied. One more small concept in the reverse bias is left, that is the transition capacitance. The capacitance that is going to be offered, otherwise the capacitance exhibited under the reverse bias condition. As the depletion region has deposited with the charges, the charges itself is going to act as the capacitance there. Okay, so it is also having some capacitance property inside the diode under reverse bias condition. We'll start tomorrow's class with that topic, and we will proceed with the characteristics of a diode. That means forward bias characteristics and reverse bias characteristics. How to plot that graph and all. We'll be studying in the next class. Okay. So this is all about today's class, students. Thank you.